Hi, everyone. Thank you for coming. So we've probably heard about a lot of bad news this morning. Impossibility, impossibility, impossibility. So now let me bring us some hope. I'm going to show you how we design incentive-compatible transaction fee mechanisms with cryptography and how we get a positive minor revenue. So I assume you've already got a lot of basics about transaction fee mechanism this morning. Just to do a brief recap. Transaction fee mechanism is basically an auction where users who want to store their transactions in the block, they compete with each other to get their transactions confirmed. So here we assume that each user has a private true value, which represents the maximum amount it is willing to pay. So the miner who controls the block, it acts as the auctioneer. It sells the space of the block to the users. So basically, this transaction fee mechanism decides which bits to confirm, how much they pay, and how much the miner gets. Due to this decentralized environment, the strategy space of transaction fee mechanism is significantly different from the classical auctions we are familiar with. First price auction, second price auction, etc. So here, a miner can inject fake bids, and the miner may not even implement the mechanism honestly. It can censor the bids. A user can also bid untruthfully, and a user can also inject fake bids. So due to all these challenges emerged in decentralized applications, we hope that an ideal transaction fee mechanism should satisfy the following three properties. User incentive compatibility, UIC. A user is incentivized to bid its true value. Miner incentive compatibility, MIC. A miner is incentivized to behave honestly, to implement the mechanism honestly and not to inject fake bids. And C-side contract proofness. If the miner includes with at least one and up to C number of users, then this miner user coalition is also incentivized.
Can you move over so you can front of the mic?
Oh.
Or point the mic towards you.
Sure.
Yeah, look that, the other one too, if you want to point. There we go, so we can hear you on the, yeah. Wherever you stand, just point the mic towards you.
Okay, thank you.
Okay.
Yeah, so for this, such a minor user coalition is also incentivized to behave honestly. So for simplicity in this talk, I'm gonna talk about the results where C equal to 1. So minor include with only one user. Unfortunately, we have learned from last talk that there is no non-trivial transaction fee mechanism that satisfies all three properties. So this is quite pessimistic. So we ask, can we circumvent this impossibility result? And the answer is yes. We can circumvent it with cryptographic techniques. So specifically, we showed that cryptography helps. We introduced a new model called the multi-party computation assisted model, or MPC assisted model for short. This model, it guarantees honest implementation of the transaction fee mechanism. And I will show you one that satisfies all three properties under this MPC assisted model. But cryptography is not a panacea. It doesn't help that much. Actually, even with this guaranteed honest implementation, we show that any transaction fee mechanism satisfying all three properties must not have a positive minor revenue. So all payments must be burned. This is not good. We still want to give the miners some positive reward to incentivize them to do the job for us. Therefore, in the follow-up work, we showed that if we make an additional reasonable world assumption, where we assume there is at least some number of honest users, then we can get a positive and asymptotically optimal minor revenue. So the rest of this talk will be split into 4 parts. I will first introduce what is MPC assisted model, and what is a good transaction fee mechanism that satisfies all three properties in this MPC assisted model, how we adapt it to achieve positive minor revenue under an additional reasonable world assumption, and finally, some exciting future directions. So how does this MPC assisted model work, and why does it help? To understand why it is helpful, it is useful to first understand the intuition behind Troansch's impossibility result. Why it is impossible to have all three properties. The main reason here is that while blockchain is a decentralized application, the implementation of transaction fee mechanism is somewhat centralized. The miner who controls the block implements the mechanism, and it can choose to implement the mechanism in an arbitrary way it prefers, in an arbitrary way that gives it the maximum profit. Therefore, to circumvent this impossibility, we ask, we're in a decentralized application. Given that there are so many miners in the whole blockchain system, why don't we also decentralize the implementation of transaction fee mechanism and guarantee an honest implementation? This is exactly what cryptography can do. This guaranteed honest implementation can be achieved with this cool technique called multi-party computation. So now let me show you how this MPCL system model works, and in my next slide, I will show you how to abstract the cryptography out for a better understanding. So in MPCL system model, instead of having a single miner implement the mechanism, we let a group of miners together to implement the mechanism. To do this, we first let the users send their bits to the miners in a secret form. If you're familiar with cryptography, they send their bits using verifiable secret sharing. Now, upon receiving this information, the miners then interact among themselves to run a cryptographic primitive called multi-party computation. Cryptography guarantees that as long as we have honest majority among this group of miners, we are guaranteed that at the end of the computation, we get the correct output of the transaction fee mechanism. So this model guarantees honest implementation of the mechanism. So to better understand this model in this talk, let's forget about the fancy cryptography. Let's think of this MPCL system model as a model that restricts the strategy space. So now we have several miners involved in this mechanism, but they cannot choose how to implement the mechanism. It is guaranteed to be implemented honestly. But still, they can inject fake bits, and still we care about incentive compatibility against individual users, against miners, and against miner user coalition, which now may contain several miners. So although MPCL system model guarantees honest implementation, it does not just reduce the problem to a classical auction design. So now with this guaranteed honest implementation, let me show you what is a good transaction fee mechanism. It is very simple. It is a posted price auction with random selection. So here we have a predetermined take it or leave it offer called the posted price. If you bid at least the posted price, you will be treated eligible. And if you bid lower than the posted price, you will never be confirmed. This mechanism just randomly chooses K eligible bids to confirm, where this K is the block size, and each confirmed bid pay the posted price. All payments are earned. So let me briefly explain why it satisfies all three properties. First, user incentive compatibility. Matt just explained it, but I'm gonna explain it again. So roughly speaking, if my true value is above the posted price, it doesn't make sense for me to bid something lower. And if my true value is below the posted price, but I bid something higher than the posted price, I will need to pay that posted price once that gets confirmed, which is even higher than my true value, the maximum amount I'm willing to pay. So a user is incentivized to bid its true value. Miner incentive compatibility is trivial. Miner's revenue is always zero. There's nothing it can do. One-side contract proofness, incentive compatibility against miner user coalition. In this coalition, since miner revenue is always zero, for them to increase their joint utility, they can only try to increase the user's utility. But the user cannot help itself because of user incentive compatibility, and the miner cannot help either because they can only inject fake bits. That will only decrease the probability of the user getting in. Therefore, this coalition does not have a strategy to increase their joint gain. So this mechanism is good. It's simple. It satisfies all three properties in the MPCL system model, so we circumvent the previous impossibility result. We get some hope here. However, it burned odd payment. Unfortunately, we proved that this burning is necessary. Miner revenue must be zero if we want to satisfy all three properties. The intuition here is simple. Let's imagine what would happen if we give the miner all the payments. Let's say for simplicity, the block size is 1 and posted price is 5. Every user's true value is below the posted price. Now the miner just reach out to a user and ask, can you just please bid 5? I'll pay you 2 cash back. The user said, okay, I'll bid 5. It pays 5 to the miner. Miner pays 2 cash back, so miner gets 3 in total. This user, it gets confirmed, and it only pays 3 for that. Everyone is strictly happier. So this breaks side contract proofness. And in general, we cannot give the miner any positive revenue. Otherwise, there will exist some scenarios where they can collude with users to increase their join gain. But this is not good. We want to pay the miner at least some positive amount to appreciate their job. So we ask, can we get a positive miner revenue if we make some reasonable additional assumptions? In the intuition I just described, the miner should not be able to derive a positive reward from any single user because they may collude. So we ask, okay, what if we assume there is at least some honest users who do not collude with the miner? Indeed, under this additional assumption, we show that we can design a transaction fee mechanism satisfying all three properties, as well as a positive and asymptotically optimal miner revenue. So to convey the main idea, I will start with the special case where we assume there is only at least one honest user. And if time allows, I will briefly show you how to generalize the idea to arbitrary h. So in this reasonable world assumption, we assume that there is at least one honest user. And we assume that the honest user's true values are IID sampled from some uniform distribution D. So this mechanism will make use of a second bonus of the MPC assistant model that hides the honest user's bid. Recall that in the MPC assistant model, users send their bids to the miners in a secret manner. This guarantees that all strategic players must decide their strategies without knowing honest users' bid. So now with this bonus, let me present to you this parity-based mechanism. For simplicity, let's say the honest user's true values are IID sampled from a uniform distribution between 0 and 1. So we set the posted price R to be the median, 0.5. Still, we randomly choose K eligible bids to confirm where this K is the block size, and each confirmed bid paid the posted price, 0.5. So till this point, from a user's perspective, this is exactly the same as random posted price with random selection. So it is user incentive compatible. The problem is, how do we determine miner revenue? We don't want to burn all the payments. So we say, okay, if the number of eligible bids among the input is odd, the miner gets one copy of the posted price. Otherwise, miner gets 0. So now let me briefly explain why it satisfies one SCP, why a miner user coalition cannot increase their join gain. The crux there is that the honest user's bid B is kept hidden from the coalition. Therefore, from the coalition's perspective, from their view, the probability that this B is eligible is exactly half. That is to say, no matter how this coalition bids, the probability that there is an odd number of eligible bids is always half, where this probability is taken over honest users' true values. Equivalently, this is saying, okay, no matter how the coalition bids, the expected miner revenue is always half times R. It doesn't change. Therefore, again, by a similar reasoning as before, for this coalition to increase their join utility, they can only try to increase the user's utility, but they cannot do that. Therefore, this parity-based mechanism, it satisfies all three properties we want, and it achieves a positive miner revenue. Of course, since now we only assume that there is at least one honest user, so we give the miner one copy of the posted price. What if we assume that there is at least more number of honest users? So to generalize this idea, the main point, the only difference is here, is really how do we determine miner revenue? From the proof sketch I just described, the crux here is to make sure that no matter how the coalition bids, expected miner revenue does not change. And we show that this goal can actually be transferred into a linear program. And formally, as long as this linear program has a solution, we have a transaction fee mechanism that satisfies all three properties, and it achieves an expected miner revenue equals to 1/4 times the minimum of H and block size, where this H is the lower bound on the number of honest users we have, times the median of distribution D. And we prove that this is asymptotically optimal. So just to wrap up, this transaction fee mechanism is still in its very early age, and there are many exciting future directions. In this talk, we've assumed a very simple model where every user's transactions are of the same size, and we don't care about the orders, we focus on just this single block. But in practice, the model is more complicated. Users' transactions are of different sizes, order actually matters, and such transaction fee mechanism is actually running repeatedly over the time. So there may exist some long-term strategies. And also, there are other interesting decentralized applications like decentralized exchange, and how do we design mechanisms for these other decentralized applications. So that completes my talk, and I'm happy to take any question.
Hey, quick follow-up to make sure I understood Hal's comment from the previous talk. So you said your mechanism is one SCP.
Yes.
You said, and did you say that two SCP is not possible even in this model?
Yeah, so the reason 2 SCP is impossible is that, let's say we two are the users in a coalition. I have a transaction worth, let's say posted price is 5, and I have a transaction worth 5 to me. You have a transaction worth 1 million. So now it doesn't make sense for me to join this round of auction. I just want to drop off. To make sure that, to increase your probability of getting confirmed. So due to this reason, it is impossible to achieve a transaction fee mechanism in MPC assisted model that is UIC, MIC, 2 SCP, and positive user social welfare. So if we want to achieve 2 SCP, user social welfare must be 0.
Got it. And can I ask a second question? Is so in your model, if I, a user, were to insert my own fake bids,
Yes.
that would not increase my probability of getting confirmed because it's like only my initial real bid is the one I want to get confirmed, and the other fake bids, if they get confirmed, they're not my real transaction.
Yes, yes.
Okay.
In our model, like when we talk about fake bids, they have 0 intrinsic value.
Got it. Cool. Thank you.
Thank you.
So we've been talking about collusion. I promise I didn't collude with Matt. He's just like 10 steps ahead of me always, and unsurprisingly anticipated my questions. So I'm curious about this last bit about different size orders and repeating nature. And what I have in mind is, like, suppose I observe 2 swap transactions at an automated exchange, and one is willing to tolerate more slippage. Like, they're willing to pay someone to front run them more than someone else. There's information in their demand for priority
Yes.
that's not hidden from their bid, which you're having them submit separately. Then the explicit fee for the transaction is hidden, but there's still information in the nature of their transaction. So I was thinking about MEV and transaction fee mechanism.
Yes.
Like, can you handle like a non-random correlation between their desire to bid? Like, if you had some information that this bid is more likely to be higher or lower, can your mechanism handle that or not?
I think the current mechanism presented in this talk does not handle that directly. Okay. But I think our MPC assisted model is actually trying to capture that, because in our if we consider, let's say for now, we forget about efficiency stuff. So in the full-fledged MPC assisted model, users can encrypt their transactions and their bid and submit to the miner. So miner probably has no information about the transaction and about the bid. So basically, we can view our MPC assisted model as a very general abstraction for techniques like encrypted mempool, where we really want to hide the information from the users.
I see. So this is like the design of a whole chain where everything is MPC assisted, not you just add this as an EIP to Ethereum and hope no one is adding information leakage through their transactions on their activities.
Yeah, actually, if we're really going to implement this MPC assessment model in practice, we will need to implement into the consensus layer. So the consensus need to be changed a little bit.
Very interesting.
So I would say it is also a very interesting future direction to see how we can come up with a more practical implementation of this MPC assessment model.
Any other questions? No? Okay, thank you very much, Ke.
Thank you so much.